all of you can give your attendance in the chat box. I repeat, all of you can give your attendance in the chat box. Can anyone please inform me whether the slides are visible to you or not?
Yes, sir. Visible, sir.
Yes, sir,
Yes, sir.
visible.
Visible.
Okay, thank you. So if you remember, in the last class we were solving some problems related to the potential energy approach, that is how to get the stiffness matrix for a particular problem that we were discussing from past few classes. Today we will solve one more problem related to that category, and then we will move on to the next topic of this module. Fine. So let us solve the fourth and the last problem related to potential energy approach. The problem is this one, this fourth problem. Let us read the problem first. The problem is telling us determine the displacements of node 1 and 2 in the spring system shown in the figure. Use minimum of potential energy principle to assemble the equations of equilibrium. That means what is given in the problem? Three springs are there in the problem, having stiffness values K1 equal to 60 Newton per meter, K2 equal to 75 Newton per meter, and K3 equal to 100 Newton per meter. Fine. This is node 1 and this is node 2. At node 1, a compressive force is applied, that is 100 Newton, and at node 2, a force of 80 Newton is applied. What I need to find out by the principle of potential energy approach, I have to find out the displacement of node 1 and displacement of node 2. Is the problem clear to all of you? If anyone can respond whether the problem is clear to all of you or not.
Yes, sir.
Okay. So before starting the problem, first of all, let us identify there are total how many nodes are present in the problem and how many elements are there. So can anyone tell me how many elements are present in the problem? Total number of elements?
Sir, 3.
Three elements. Very good. This is your element number 1. This is the first element. This is the second element, and this is the third element. And can anyone tell me how many number of nodes are present in the problem? Can anyone tell me how many number of nodes are present in the problem?
So is it 2?
Technically, if you say there are total 4 nodes, 1, 2, 3, 4, but I will not take these 2 nodes into account. Why I will not take these 2 nodes into account?
Sir,
That displacement is 0.
Yes, because I can see that this first element, second element, and the third element, this entire system is connected at this end as well as at this end. So whatever force you apply at each and every node, displacement of this end and this end is 0. So that's why I am not considering this particular node and this particular node. So I can say that in this problem 1, 2, 3 elements are there and there are total 2 nodes. Obviously, two more nodes are there, but their displacement is 0. Is it clear now? Hello.
Yes, sir.
Okay. So by potential energy approach, first of all, what I need to find out? I need to find out the potential energy of the complete system. I know that potential energy pi is given by summation of internal energy plus the summation of all external energy stored in the system. Internal energy is nothing but the strain energy stored in the system, and I know that if there is any spring element is there, then the strain energy stored in the spring element is given by the expression u is equal to half k into delta square, where k is the stiffness of the spring and delta is the deflection of the spring due to nodal forces. So u is equal to half k into delta square, equation number 2. Now if you see, this equation number 2 will have three components. This equation number 2 will have three components. That means for this particular element, assume that the deflection is delta 1. For the second element, assume that the deflection is delta 2. For the third element, assume that the deflection is delta 3. Then overall strain energy for the entire system will be how much? It will be half k1 delta 1 square plus half k2 delta 2 square plus half k3 delta 3 square. Is it clear?
Yes, sir.
So first let us find out the values of these deflection delta 1, delta 2 and delta 3. Let us find out. If you see, this first element is connected with node 1 and with this fixed support. So the linear displacement of the first element will be equal to deflection u1. Assume that at this nodal point deflection is u1. At this second nodal point deflection is u2. Deflection u2, deflection u1. Then the first element can deflect by an amount u1 along this direction, yes or no?
Yes, sir.
That means delta 1 is equal to u1. Similarly, for second element, since this end is fixed, the overall linear displacement of this second element is also equal to u1, because both first and the second element are connected in, they are connected in parallel. So the displacement will be same for second element also. That means for second element delta 2 is again equal to u1. Yes or no?
Yes, sir.
Other people please respond whether it is clear or not. Delta 1 is equal to u1 and delta 2 is equal to u1. Other people please respond. Hello. If you will not respond, how I will understood that you have understood the problem? I cannot move forward. So you have to say whether you have understood or not. Krishanu,
Yes, sir.
Jyotirmoy,
Clear.
Umesh,
Yes,
please respond.
yes, sir. Understood.
Yes, sir.
Okay. So next is the deflection of this particular element, that is delta 3. Deflection of this particular element delta 3. I can clearly see that this particular element is connected between node 1 and node 2, and the entire system is moving along this end. So if I assume that this f2 is greater than f1, then the overall displacement delta 3 will be what? It will be u2 minus u1. U2 is deflection of this end and u1 is deflection of this end. Then I can write delta 3 equal to u2 minus u1. Yes or no?
Sir, at
Yes, sir.
node 2, sir, at 2 the force is less now. So it should be u1 minus u2 now.
No, see, you If you write u1 minus u2, that is also correct. I have written it u2 minus u1. At last, what will happen? At last, your final value of delta 3, if it is coming positive, that means you have taken the direction in correct manner. If your value of delta 3 is negative, that means you have taken the wrong direction. Direction will be in opposite direction. Just for solving the problem, I have to take one direction.
Okay, sir.
So that's why I have assumed, since the entire system is moving towards positive x-axis, so I am assuming that whatever force is acting along in this direction, that is greater than the previous one. So is it okay now?
Yes, sir.
Okay. So delta 3 is u2 minus u1. Now I will substitute.
सर
Yes.
डेल्टा वन और डेल्टा टू का वैल्यू सेम है U1
Yes. Value of delta 1 and value of delta 2 is same. Why same? Because see, this end is fixed, this end is fixed. Displacement of node 1 is u1. So maximum deflection of this element along this direction is how much? It is u1 only, u1 minus this node deflection, and this node deflection is 0. Similarly, for this element, maximum deflection is how much? That is u1 minus this node displacement, and this node displacement is 0, so it is equal to u1. Yes or no? Fine. So now what we will do is we will substitute the value of delta 1, delta 2 and delta 3 in this expression. U is equal to half k1 delta 1 square plus half k2 delta 2 square plus half k3 delta 3 square. Let us substitute. The final expression of U becomes U is equal to half k1 delta 1 is u1 plus half k2 delta 2 is again u1 plus half k3 delta 3 is u2 minus u1 whole square, which is equation number 3. Any doubt till equation number 3?
No, sir.
Okay. So we have found out the value of internal energy. Now we need to find out the value of external energy. We know that external energy is nothing but the external work done on the system. And in this problem, it is very much clear that only external work is being done on the system due to the presence of point load, and that point load is acting at node 1 and at node 2. So the work done by point load is given by what? It is given by, and since this work done is negative, so it is minus summation of point load into displacement at that particular node where the force is acting. This I represent the nodal point where F is acting. From this diagram, it is very much clear that the point load is acting at nodal point 1 and nodal point 2. So the value of W will be minus F is 100 into U1 because it is acting at nodal point 1 minus F, that is 80 into U2 because this 80 is acting at nodal point 2. So the value of W becomes minus 100 U1 minus 80 U2. Equation number 4. Is it clear?
Yes, sir.
Okay, so now what I will do is I will substitute this equation number 3 and equation number 4 in equation number 1. That means I am substituting the value of U and W from 3 and 4 in 1. If you substitute, the final potential energy for this system comes out to be pi is equal to half k1 u1 square plus half k2 u1 square plus half k3 u2 minus u1 whole square minus 100 u1 minus 80 u2. That is equation number 5. Is it clear?
yes sir
Yes, sir, clear.
Okay, now I have to use the principle of potential energy. According to the principle of potential energy, if I need to keep the entire system in equilibrium, what I need to do? I need to minimize the value of this potential energy. I need to minimize equation number 5. How I can minimize? I have to partially differentiate this equation number 5 with respect to unknown displacement present in the problem. There are total two unknown displacement present in the problem, that is u1 at node 1 and u2 at node 2. So first time we will partially differentiate equation number 5 with respect to u1, that is del pi by del u1 equal to 0. You will get one equation. Second time, again you will partially differentiate equation number 5 with respect to u2 and equate it equal to 0. That is del pi by del u2 equal to 0. You will get one equation. Then at last, you will write these two equations in matrix form and just solve that matrix equation. You will get the value of u1 and u2. So first, let us differentiate equation number 5 partially with respect to u1 and equate it to 0. That is del pi by del u1 equal to 0. Just partially differentiate equation number 5 with respect to u1. If you differentiate it, you will get equation number A, that is K1 plus K2 plus K3 times of U1 minus K3 times of U2 equal to 100. Is it clear? Equation number A. Any doubt in equation number A so far?
No,
Yes,
sir.
sir.
Okay. Second time, again we will partially differentiate equation number 5 with respect to u2 and equate it equal to 0. So del by del u2 of pi equal to 0. If you partially differentiate it, you will get equation number B, that is minus k3u1 plus k3u2 equal to 80. I am not showing you the steps because this you can do it. You have did this partial differentiation thing in mathematics, so you can easily differentiate it. I am not explaining it further. So is it clear equation number A and equation number B? Any doubt?
Yes, sir.
Okay. And I also know the governing algebraic equation for this problem is what? Governing algebraic equation for this problem is F is equal to K into delta, and this F is known as restoring force with which the spring will bounce back to its original position. If I write this equation, governing algebraic equation in matrix form, how I can write? This matrix F is equal to matrix K into matrix delta. See, that is K matrix into U matrix is equal to F matrix. This K matrix is known as stiffness, global stiffness matrix for this particular problem. What is this U? This U is known as displacement field vector, and what is this F is your nodal force vector. So writing equation A and B in this form, let us write. So I know that since there are total two nodes present in this problem. Obviously, the third and the fourth nodal point is deflection is 0, so I will not consider it. There are two nodes present in the problem, and we have learned from the last class that the overall stiffness matrix will be a 2 cross 2 stiffness matrix. Number of nodes is equal to the number of stiffness number is equal to the order of that stiffness matrix. Fine. So I know that the stiffness matrix will be of order 2 cross 2. So, and I also know from the last lecture that I also know from the last lecture that since it is a 2 cross 2 matrix, this first row represent coefficient of u1, first row and first column. Similarly, second row and second column represents coefficient of displacement u2. See, because u1 is applied at the first nodal point and u2 is applied at the second nodal point. So inside matrix, whatever thing we will write, we will keep in mind that from equation number A and B, this first row is represents the coefficient of u1. Second row, coefficient of u2. First column and second column represent coefficient of u1 and u2 respectively. So let us then the displacement vector will be along first row. Displacement is u1, write u1 over here. Again along second row the displacement is u2, write u2, which is equal to, at the first nodal point, how much is the force acting? Force acting is plus 100 Newton in positive x direction, and at the second nodal point it is plus 80 Newton. So substitute, see, 180. Now inside this stiffness matrix I have to substitute the values. Let us substitute. So from equation number A, coefficient of u1 is k1 plus k2 plus k3. Write down k1 plus k2 plus k3. Here this is coefficient of u2 from equation number A. From equation number A, coefficient of u2 is minus k3. Minus k3. Along second row, this is coefficient of u1, this is coefficient of u2 for equation number B. For equation number B. So coefficient of u1 is minus k3, and coefficient of u2 is k3, k3. So the resulting matrix becomes k1 plus k2 plus k3 minus k3 minus k3 k3 into column matrix u1 u2 equal to column matrix 180. Now since k1 k2 and k3 is given in the problem, I can substitute the values. After substituting the values of k1 k2 and k3, the resulting matrix becomes 235 minus 100 into u1 u2 equal to 100 into 80. So I need to find out the value of u1 u2. So u1 u2 will be what? Inverse of this matrix, 235 minus 100 into 180. Either you can use this technique, or what you can do, just break it. That means matrix multiplication. That means this first row into first column will be equal to 100. That is 235 u1 minus 100 u2 equal to 100. This equation. Similarly, this row into this column, if you multiply, you will get equal to 80. So minus 100 into u1 plus 100 into u2 equal to 80. You are having two equations, two unknown. You will get the value of u1 and u2, and that is coming out to be 1.33 meter. That is displacement of first nodal point is 1.33 meter, and displacement of second nodal point is 2.13 meter by this potential energy approach. Any doubt in this problem?
No, sir.
Okay. Other people, please respond whether this problem is clear or not.
No, sir. No.
Okay. So you can expect such kind of problems in your examination. What will happen is that what I can do is I can increase the number of element. Here 3 springs are there. I can give you a 10 spring problem. I can give you an 8 spring problem. I can give you a 7 spring problem likewise. But the procedure will be similar. Okay. Should I move forward?
Yes, sir.
Okay, so with this we have completed the first subtopic of the second module. Now we are moving on to the second subtopic of this second module, and that is determination of stiffness matrix by direct stiffness method. If you remember, so far we have found out the stiffness matrix value for a problem by potential energy approach, but now we will be using direct stiffness method to find out the value of this stiffness matrix. This stiffness matrix now we will find out by direct stiffness method. So first of all, let us take the very simplest case. That is when one element is present. When there is one element, how to get the stiffness matrix of this particular element by direct stiffness method. So from the diagram, it is very much clear that only one element is present, and that element is having the stiffness value equal to Ke. Ke means stiffness of this particular element. And this element is connected by two nodes, node 1 and node 2. At node 1, the nodal force and the nodal displacement vector is F1 and U1. Similarly, at node 2, the nodal forces and nodal displacement values are F2 and U2. Is it clear? So far, any doubt?
Yes, sir.
So due to this nodal force F1 and F2, this element will deflect linearly. So first of all, we have to find out that deflection value, and that deflection will be what? That deflection is, if I assume that F2 at node 2 is greater than F1 at node 1, then the linear displacement delta will be what? It will be U2 minus U1. That is equation number 1. Is it okay?
Yes, sir.
I also know that the governing algebraic equation for one dimensional spring element is given by what? F is equal to K into delta. For this element, delta is nothing but this value. For this element, K is what? Stiffness of the element, that is K element. So I can write this equation as F is equal to stiffness of the element into delta, that is linear deflection of the element. Yes or no?
Yes, sir.
Hello. Fine. Since we have found out the value of delta, so we can substitute the value of delta over here. If you substitute, the final expression of F becomes F is equal to K E, that is stiffness for this particular element, into delta. Delta is how much? U2 minus U1. So I will get equation number 3, that is F is equal to K into U2 minus U1. Is it okay?
Yes, sir.
Other people, please respond whether it is clear or not. Other people, please respond whether it is clear or not.
Yes, sir.
Yes, sir.
Fine. So this is the governing algebraic equation for this particular element. Now, if I want to keep this element in equilibrium condition, I have to use the equations of equilibrium. That is, the summation of all the forces along x direction is equal to 0. And this f summation of fx for this particular problem will be what? It will be f1 plus f2 along positive x direction. So f1 plus f2 equal to 0. So I can write f1 is equal to minus times of f2, or f2 is equal to minus times of f1. That is equation number 4. Is it clear?
Yes, sir.
Fine. In this method, I will not be using the potential energy approach. That means I am not interested in finding out the value of strain energy. Neither I am interested in finding out the value of the external work done. I have to use this method called direct stiffness method or matrix method. So since I got F1 is equal to minus F2, then for this particular element, I can write the value of F1 and F2. If I assume that F2 is greater than F1, then F2, that is F1 and F2, how I can write? F2 is equal to what? F2 is stiffness K into deflection. Assume that at this point deflection is what? U2 minus U1. If at node 2 deflection is U2 minus U1, since F2 is greater than F1, then at node 1 we know that F2 is minus times of F1. F2 is minus times of F1. So then the deflection will be what? Deflection will be U1 minus U2 at node 1. Yes or no? That means minus times of U2 minus U1, and it will be U1 minus U2. Yes or no?
Yes, sir.
Fine. So F1 is minus K u2 minus u1, and f2 is k u2 minus u1. Fine. Which is equation number 5. I can write equation number 5 more precisely as f1 is equal to minus k u2 minus minus plus k u1, and f2 is equal to k u2 minus k u1. Now, if I want to write this equation number 6 in matrix form, how I can write? Stiffness matrix into displacement vector matrix equal to nodal force matrix. Now this K
Sir,
stiffness matrix will be what?
excuse me, sir.
Yes.
सर इक्वेशन 5 टा एक बार बोले और एक बार बता दीजिए ना.
Equation number 5. Okay. If I draw the free body diagram of this element, if I draw the free body diagram of this element, this is what? This is the element. At this nodal point, F2 is acting. F2 is acting at second nodal point, and at first nodal point, F1 is acting at first nodal point. If I want to keep this element in equilibrium, I have to use the equations of equilibrium, and that will be f summation of fx equal to 0. All the forces are along positive x direction, so I can write f1 plus f2 equal to 0, or I can write f1 is equal to minus f2, or f2 is equal to minus f1. Is it clear so far?
Yes, sir, of clear है sir.
Is it
Continue.
clear? Now,
Yes.
I have the governing differential equation as f is equal to k into delta. Delta already we have found out for this element. So I can write f is equal to k into delta. Delta is what? u2 minus u1. If f2 is greater than f1, then delta will be u2 minus u1. If f1 is greater than f2, then you have to put a minus sign. If you put a minus sign, then f1 will become minus k what? u2 minus u1, or I can write it as k u1 minus u2. Yes or no?
Yes,
Yes,
sir.
sir.
Fine. So f1 is minus k u2 minus u1, or k u1 minus u2, and f2 is k u2 minus u1. So just expand equation number 5, you will get equation number 6. And I have told you previously also that the size of the stiffness matrix depends upon the total number of nodes present in the problem. In this problem, how many number of nodes are present? Total 2 nodes are present. In this problem, total 2
Two nodes
nodes
is
are
there.
present. So the size of the stiffness matrix will be a 2 cross 2 matrix. Yes or no? Size of the stiffness
Sir.
matrix is 2 cross 2 matrix. So this is one, two rows, two column, and I also know that this first row and first column represent the coefficient of u1, because u1 is present at first node, and this second row and second column of this stiffness matrix represent the coefficient of u2, because u2 is present at second nodal point. Are you getting my point?
Yes, sir. Yes, sir. I'm
Fine.
getting.
And this first row is nothing but this equation number, this equation, which equation? This particular equation. And the second row is nothing but this particular equation. So I am just writing these two equations in matrix form. Let us write. So this is what? This is the, for first equation, coefficient of u1. Coefficient of u1 is plus k. This is for the first equation, coefficient of u2, that is minus k. So k minus k. This value is coefficient of u1 from the second equation. So from the second equation, coefficient of u1 is minus k. So minus k, and this value is what? This value is the coefficient of u2 from the second equation, and that is nothing but k. So k into column matrix. Since two nodes are present, so there will be two displacement, that is u1, u2, equal to column matrix nodal force vector. Since for at nodal point 1 force F1 is acting, at nodal point 2 force F2 is acting, and I have clearly told you that this is for the first node, this is for the second node. Since for first node F1 is acting, direction is in positive x direction, so this is plus F1. For second node, the force acting is F2. That is also it is acting along positive x direction. So I will take plus F2. So the final resulting matrix becomes K minus K into U1 U2 equal to F1 F2. Is this equation clear to all of you? That is this particular matrix equation. Is it clear to all of you?
Yes, sir.
Other people also respond whether it is clear or not.
Yes, sir, clear.
Fine. So in this expression, this particular, see, this KE is what? This term. This U is this term and this F is this term. So this particular term, that is KE, is known as the global stiffness matrix. Global element stiffness matrix for this particular element by direct stiffness method. See here, nowhere I have used the potential energy concept. I have just used the mechanics concept, and I have framed two equations because two nodes are present. Two equations I have framed, algebraic equations. Then I have converted that algebraic equations into a matrix equation. From this matrix equations, I can conclude that yes, this particular term is your global stiffness matrix. This particular term is your displacement vector, and this particular term is your nodal force vector. So this is one more way to find out the global element stiffness matrix by direct stiffness method. Any doubt in this method? Any doubt in this method? Hello?
No,
Sir,
sir.
Other
sir,
people
if
please respond whether this method is clear or not.
sir, if someone choose, hello, sir.
Yes?
Sir, if someone do this problem by potential energy method, the result will be
No,
same,
but if
right?
in the exam I give you that use direct stiffness method to derive a matrix, to derive the global element stiffness matrix, then you cannot use. And if you are using say potential energy approach, then by that approach, how you can solve? For that you have to find out the value of u. U is what? U is half k into delta square. Delta is u2 minus u1. So u is half k in bracket u2 minus u1 square. This is u. You have to find out the value of w. W will be what? W will be minus f1 u1 minus f2 u2, then add u with w. This is your pi, and since at nodal point 1 this displacement 1 u1 is present, at nodal point 2 this displacement u2 is present, you have to minimize pi. That means del pi by del u1 is equal to 0. You will get one equation. Again you will get the same expression. If you do del pi by del u2 equal to 0, again you will get the same f2 expression. Then write it in the matrix form. Ultimately, whether you use potential energy approach or you use direct stiffness method, you will get the same global element stiffness matrix. There is no change in the expression of global element stiffness matrix, but the way of solving the problem is different. Are you getting my point?
Yes, sir.
Are
Now
you
I
getting
get.
my point? So if I am not giving you, if I have told you, say I have given you this problem, which problem? Say I have given you this problem, and I have told you that derive the global element stiffness matrix for this problem. You can use any method, but if I have mentioned you clearly that use direct stiffness method, then you have to use direct stiffness method for this problem, or use potential energy method, then you have to use potential energy method. Yes or no?
Yes, sir.
Fine. Okay. So this is very simple problem because here I have taken only one element comprising of two nodes. I can solve this particular problem. I can solve this particular problem by direct stiffness method also. Yes or no?
Yes, sir.
Then for if I solve this problem by direct stiffness method, can you tell me the size of global stiffness matrix? Order of the global stiffness matrix, what will be the order? If you have understood the concept, what will be the
Four
order
comma
of
four.
the global
In
stiffness
4 cross
matrix?
4.
Sorry?
4
4
by
cross
4.
Yes, 4 by 4. Why? Because total 4 nodes are there. 1, 2, 3, 4. So I will get a big stiffness matrix of 4 cross 4. Uh, see, 4 cross 4 matrix we have got by potential energy approach. The same problem you solve it by direct stiffness approach. Okay. You will get the same answer. There is no change in the answer. But the way of solving is different. Okay. Hello.
Yes, sir.
Yes, sir.
Fine. Similarly, I can solve this problem. I can solve this problem also by direct stiffness method. Now tell me, if I solve this problem by direct stiffness method, tell me the order of the final global stiffness matrix. Tell me the order of the final global stiffness matrix. What is the order of the final global stiffness matrix?
सर यहाँ पे जो स्प्रिंग्स पैरेलल में है वो क्या एक सिंगल स्प्रिंग बनेगा ना कॉम्बिनेशन के बाद
Every
इक्विवेलेंट स्प्रिंग
string is
बनेगा
an element. You here you will not use the concept of parallel or series. You have
ओके
to, if there are 20 springs present, that means 20 elements are there.
ओके
So
सर ओके
now tell me what will be
5 cross
the order of the final global stiffness matrix?
5 cross 5.
5 cross
Because
5. No, no. It will be 3 cross 3. How it will be 3 cross 3? See, this is one node, this is second node, this is third node, this is fourth node. Is it clear that in this problem there are 4 nodes are present?
एक बार फिर से repeat.
This is first node, this is second node, this is third node, and this is fourth node. Is it clear to all of you?
Yes, sir. Clear now.
And if you see the elements, this is first element, second element, third element, fourth element, fifth element. Okay. And if you see, the displacement of this node is 0. Displacement of this node is always 0. So why to consider this node then? Then my node becomes, this is node 1, node 2, node 3. Element 1 is connected between fixed node and node 1. Element 3 is connected between node 1 and node 3. 2 is between node 1 and node 2. 4 and 5 is between node 2 and node 3. So ultimately there are 3 nodes present. Is it clear?
Because see all.
So the final global stiffness matrix will be a 3 cross 3 matrix if I use this direct stiffness method. If I use this direct stiffness method, it will be a 3 cross 3 matrix. Is it clear?
Yes, sir. Clear.
Other people, please respond whether it is clear or not.
Yes, sir. Clear.
Okay, fine. So today I don't think enough time is left. So what we will do is that in the next class, we will solve some typical problems. That means we will try to find out the global stiffness matrix of some typical problems containing more than one element. Okay. So with this, what I do is I will end my today's lecture over here. Again, we will meet in the next class. If anyone is having any kind of doubt in today's lecture, you can ask me, or else you can leave the class. And Krishanu, you were telling that the PPT is not visible,
Yes,
but
sir, it is okay now. It is
I
okay.
have checked it thoroughly. It is completely visible.
Yes, sir, now it's okay.
It is completely visible. I have given all the recorded lectures as well as the PPT of first module. Also, I have given some 1 or 2 recorded lectures of this second module. So you all can see those lectures. Okay, then if anyone is left to give the attendance, you can give it, or else you can leave the meeting. Thank you.
Thank you, sir.
Welcome.
Thank you, sir.